Okay, so the next part of our lesson regarding second order differential equations is going to be about solving them. Okay, so let's refresh on the standard general form for second order linear ODE. Okay, so it is y double prime plus p of t y prime plus q of t y equals r of t. So how do we solve this? How do we solve this? Well, to start by solving this, we should simplify and look at a pretty basic scenario. So simplify, look at basic scenario. And this would be when p of t, q of t, r of t are all constants. And specifically, r of t is 0, so the equation is homogeneous. Okay, so we're not solving this thing. What we're solving is y double prime plus p y prime plus q y. Plus q y equals 0. So that is what we're solving for now. Okay, so as with any solution, we should start off with a guess. Okay, and so a guess to this, let's just throw one out there. Maybe y of t equals e to the rt. You know, that sounds plausible. The derivative of e to the t is always, e to the t. So it would make sense that maybe if you threw in e to the t, you would somehow get this to work where it would equal 0. So this is our guess. And let's see if it works. Okay, so let me just look through my notes here. Okay, so if we plug in e to the rt for y, we can differentiate. So e to the rt double prime would be r squared e to the rt. Look, I'm just differentiating this by plugging it into here. Okay, so and then p, so r e to the rt plus q e to the rt equals 0. And we can factor out an e to the rt here. So what we get is r squared plus pr plus q equals 0. Now this is a quadratic, right? And so e to the rt we know is never 0. So since this is never 0, then for this equation to be true, this has to be 0. And so what this is actually called is the characteristic polynomial. So characteristic polynomial of homogeneous second order linear ordinary differential equations with constant coefficients is this r squared plus pr plus q equals 0. And this, of course, was obtained by guessing that e to the rt was the solution, substituting that in for y within the differential equation, and factoring out the e to the rt, which leaves you with this characteristic polynomial. And so we're going to look at the implications of this characteristic polynomial in future videos, but for now, let's just think about what the possible scenarios are for this polynomial. So you're trying to solve for r, right? And it seems that like if you solve for r, then you can solve for this e to the rt term, and maybe you can solve for the general solution. Okay, so as with any polynomial, the roots have 3 cases. Okay, so we're going to look at the 3 possible cases. So case 1, the discriminant, which would be p squared minus 4q, is positive, which signifies that there are 2 real roots. Case 2, discriminant is negative, and so there are 2 complex / imaginary, oh gosh, I spelled that wrong, imaginary roots. And then the last case, case 3, is that the discriminant is equal to 0. And so there is only 1 real root.